Exponentiation is a mathematical operation, written as Bn, involving two numbers, the base b and the exponent n. When n is a positive integer, exponentiation corresponds to repeated multiplication of the base. That is, Bn is the product of multiplying n bases. In that case, Bn is called the nth power of b, or b raised to the power n. The exponent is usually shown as a superscript to the right of the base. Some common exponents have their own names. The exponent 2 is called the square of b, or b squared. The exponent 3 is called the cube of b, or b cubed. The exponent -1 of b, or 1b, is called the reciprocal of b. When n is a negative integer and b is not 0, Bn is naturally defined as 1, b minus n, preserving the property Bn times Bm equals Bn plus m. The definition of exponentiation can be extended to allow any real or complex exponent. Exponentiation by integer exponents can also be defined for a wide variety of algebraic structures, including matrices. Exponentiation is used extensively in many fields, including economics, biology, chemistry, physics, and computer science, with applications such as compound interest, population growth, chemical reaction kinetics, wave behavior, and public key cryptography. History of the notation. The term power was used by the Greek mathematician Euclid for the square of a line. Archimedes discovered and proved the law of exponents, 10a 10b equals 10a plus b, necessary to manipulate powers of 10. In the 9th century, the Persian mathematician Muhammad ibn Musa al-Khwarizmi used the terms ma'al for a square and kab for a cube, which later Islamic mathematicians represented in mathematical notation as m and k, respectively, by the 15th century, as seen in the work of Abu al-Hasan ibn Ali al-Khalaysadi. In the late 16th century, Jos Bergi used Roman numerals for exponents. Early in the 17th century, the first form of our modern exponential notation was introduced by René Descartes in his text titled La Géométrie. There, the notation is introduced in Book I. Nicolas Touquet used a form of exponential notation in the 15th century, which was later used by Enrique Grammateus and Michael Stiefel in the 16th century. The word exponent was coined in 1544 by Michael Stiefel. Samuel Jeake introduced the term indices in 1696. In the 16th century, Robert Ricorder used the terms square, cube, Zenziingik, sursolid, Zenzicube, second sursolid, and Zenziingazenzik. Biquadrata has been used to refer to the fourth power as well. Some mathematicians used exponents only for powers greater than 2, preferring to represent squares as repeated multiplication. Thus they would write polynomials, for example, as x plus bx x plus cx 3 plus d. Another historical synonym, involution, is now rare and should not be confused with its more common meaning. Terminology. The expression b2 equals bb is called the square of b because the area of a square with side length b is b2. It is pronounced b squared. The expression b3 equals bbb is called the cube of b because the volume of a cube with side length b is b3. It is pronounced b cubed. The exponent indicates how many copies of the base are multiplied together. For example, 35 equals 33333 equals 243. The base 3 appears 5 times in the repeated multiplication, because the exponent is 5. Here, 3 is the base, 5 is the exponent, and 243 is the power, or, more specifically, the fifth power of 3, 3 raised to the fifth power, or 3 to the power of 5. The word raise is usually omitted, and very often power as well, so 35 is typically pronounced 3 to the fifth or 3 to the 5. The exponentiation Bn can be read as b raised to the nth power, or b raised to the power of n, or b raised by the exponent of n, or most briefly as b to the n. Exponentiation may be generalized from integer exponents to more general types of numbers. Integer exponents. The exponentiation operation with integer exponents requires only elementary algebra. Positive integer exponents. Formally, powers with positive integer exponents may be defined by the initial condition and the recurrence relation from the associativity of multiplication. It follows that for any positive integers m and n, 0 exponent, any non-zero number raised by the exponent 0 is 1. One interpretation of such a power is as an empty product. The case of OO is discussed below. Negative exponents. The following identity holds for an arbitrary integer n and non-zero b. Raising 0 by a negative exponent is left undefined. The identity above may be derived through a definition aimed at extending the range of exponents to negative integers. For non-zero b and positive n, the recurrence relation from the previous subsection can be rewritten as by defining this relation as valid for all integer n and non-zero b. It follows that, and more generally for any non-zero b and any non-negative integer n, this is then readily shown to be true for every integer n. Combinatorial interpretation for non-negative integers n and m. The power nanometer is the number of functions from a set of m elements to a set of n elements. Such functions can be represented as m tuples from an n-element set. Identities and properties. The following identities hold for all integer exponents, provided that the base is non-zero. Exponentiation is not commutative. This contrasts with addition and multiplication, which are, for example, 2 plus 3 equals 3 plus 2 equals 5 and 2 3 equals 3 2 equals 6, but 23 equals 8, whereas 32 equals 9. Exponentiation is not associative either. Addition and multiplication are, for example, plus 4 equals 2 plus equals 9 and 4 equals 2 equals 24, but 23 to the 4 is 84 or 7003409600000004096. Whereas 2 to the 34 is 281 or 70242417851639229524178292258349412352. Without parentheses to modify the order of calculation, by convention the order is top-down, not bottom-up. Note that some computer programs associate to the left instead, i.e., a(b)(c) is evaluated as (c). Particular bases powers of 10 in the base 10 number system. Integer powers of 10 are written as the digit 1 followed or preceded by a number of zeros determined by the sign and magnitude of the exponent. For example, 700310000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 10⁻4 equals 6996100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 scientific notation to denote large or small numbers. For instance, 7008299792458 meters per second can be written as 7008299792458 times 108 meters per second and then approximated as 700829980000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 SI prefixes based on powers of 10 are also used to describe powers of 10 are also used to describe small or large quantities. For example, the prefix kilo means 700310000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 so a kilometer is 70031000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000science because there are two n possible values for an n-bit binary register. Powers of 2 are important in set theory since a set with n members has a power set, or set of all subsets of the original set, with 2 n members. The negative powers of 2 are commonly used, and the first two have special names, half and quarter. In the base 2 number system, integer powers of 2 are written as 1 followed or preceded by a number of zeros determined by the sign and magnitude of the exponent. For example, 2 to the power of 3 is written as 1000 in binary. Powers of 1 of the powers of 1 are all 1. 1 n equals 1. Powers of 0 if the exponent is positive, the power of 0 is 0. 0 n equals 0, where n greater than 0. If the exponent is negative, the power of 0 is undefined, because division by 0 is implied. If the exponent is 0, some authors define O equals 1, whereas others leave it undefined, as discussed below under 0 to the power of 0. Powers of -1 if n is an even integer, then n equals 1. If n is an odd integer, then n equals -1. Because of this, powers of -1 are useful for expressing alternating sequences. For a similar discussion of powers of the complex number I, see powers of complex numbers. Large exponents, the limit of a sequence of powers of a number greater than 1 diverges. In other words, the sequence grows without bound. Bn infinity as n infinity when b greater than 1. This can be read as b to the power of n tends to plus infinity as n tends to infinity when b is greater than 1. Powers of a number with absolute value less than 1 tend to 0. Bn 0 as n infinity when b less than 1. Any power of 1 is always 1. A particularly important case is any as n infinity. See the exponential function below. Other limits, in particular of those that take on an indeterminate form, are described in limits of powers below. Rational exponents. An nth root of a number b is a number x such that xn equals b. If b is a positive real number and n is a positive integer, then there is exactly one positive real solution to xn equals b. This solution is called the principal nth root of b. It is denoted n square root b, where square root is the radical symbol. Alternatively, the principal root may be written b1, n. For example, 41 halves equals 2, 81 thirds equals 2. The fact that solves follows from noting that if n is even, then xn equals b has two real solutions if b is positive, which are the positive and negative nth roots. If b is negative, the equation has no solution in real numbers for even n. If n is odd, then xn equals b has one real solution. The solution is positive if b is positive and negative if b is negative. The principal root of a positive real number b with a rational exponent u, v in lowest terms satisfies where u is an integer and v is a positive integer. Rational powers u, v, where u, v is in lowest terms, are positive if u is even, and negative for negative b if u and v are odd. There are two roots, one of each sign, if b is positive and v is even. In this case the principal root is defined to be the positive one. Thus we have 1/3 equals -3 and 2/3 equals 9. The number 4 has two 3/2 th roots, namely 8 and -8. However, by convention 43/2 denotes the principal root, which is 8. Since there is no real number x such that x2 equals -1, the definition of v when b is negative and v is even must use the imaginary unit I, as described more fully in the section Powers of Complex Numbers. Care needs to be taken when applying the power identities with negative nth roots. For instance, minus 27 equals 2/3, 3/2 equals 93 halves equals 27 is clearly wrong. The problem here occurs in taking the positive square root rather than the negative one at the last step. But in general the same sorts of problems occur as described for complex numbers in the section Failure of Power and Logarithm Identities. Real exponents. The identities and properties shown above for integer exponents are true for positive real numbers with non-integer exponents as well. However, the identity cannot be extended consistently to cases where b is a negative real number. The failure of this identity is the basis for the problems with complex number powers detailed under Failure of Power and Logarithm Identities. Exponentiation to real powers of positive real numbers can be defined either by extending the rational powers to rails by continuity, or more usually as given in powers via logarithms below. Limits of rational exponents. Since any irrational number can be expressed as the limit of a sequence of rational numbers, exponentiation of a positive real number b with an arbitrary real exponent x can be defined by continuity with the rule where the limit as r gets close to x is taken only over rational values of r. This limit only exists for positive b. The definition of limit is used. This involves showing that for any desired accuracy of the result bx, one can choose a sufficiently small interval around x so all the rational powers in the interval are within the desired accuracy. For example, if x equals pi, the non-terminating decimal representation pi equals 3.14159 can be used to obtain the intervals bounded by rational powers. The bounded intervals converge to a unique real number, denoted by. This technique can be used to obtain any irrational power of a positive real number b. The function f b equals bx is thus defined for any real number x. The exponential function, the important mathematical constant t, sometimes called Euler's number, is approximately equal to 2.718 and is the base of the natural logarithm. Although exponentiation of e could, in principle, be treated the same as exponentiation of any other real number, such exponentials turn out to have particularly elegant and useful properties. Among other things, these properties allow exponentials of e to be generalized in a natural way to other types of exponents, such as complex numbers or even matrices, while coinciding with the familiar meaning of exponentiation with rational exponents. As a consequence, the notation x usually denotes a generalized exponentiation definition called the exponential function, exp, which can be defined in many equivalent ways, for example by, among other properties, exp satisfies the exponential identity. The exponential function is defined for all integer, fractional, real, and complex values of x. In fact, the matrix exponential is well defined for square matrices, and is useful for solving systems of linear differential equations. Since exp is equal to e and exp satisfies the exponential identity, it immediately follows that exp coincides with the repeated multiplication definition of x for integer x. And it also follows that rational powers denote roots as usual. So exp coincides with the x definitions in the previous section for all real x by continuity. Powers via logarithms. The natural logarithm lane is the inverse of the exponential function x. It is defined for b greater than 0, and satisfies if bx is to preserve the logarithm and exponent rules, then one must have for each real number x. This can be used as an alternative definition of the real number power bx and agrees with the definition given above using rational exponents and continuity. The definition of exponentiation using logarithms is more common in the context of complex numbers, as discussed below. Real exponents with negative basis powers of a positive real number are always positive real numbers. The solution of x2 equals 4, however, can be either 2 or -2. The principal value of 41/2 is 2, but -2 is also a valid square root. If the definition of exponentiation of real numbers is extended to allow negative results, then the result is no longer well behaved. Neither the logarithm method nor the rational exponent method can be used to define BR as a real number for a negative real number B and an arbitrary real number R. Indeed, is positive for every real number R, so lane is not defined as a real number for B0. The rational exponent method cannot be used for negative values of B because it relies on continuity. The function f equals BR has a unique continuous extension from the rational numbers to the real numbers for each b greater than 0. But when b less than 0, the function f is not even continuous on the set of rational numbers R for which it is defined. For example, consider b equals -1. The nth root of -1 is -1 for every odd natural number n. So if n is an odd positive integer, equals -1 if m is odd, and equals 1 if m is even. Thus the set of rational numbers q for which q equals 1 is dense in the rational numbers, as is the set of q for which q equals -1. This means that the function q is not continuous at any rational number q where it is defined. On the other hand, arbitrary complex powers of negative numbers b can be defined by choosing a complex logarithm of b. Irrational exponents. If a is a positive algebraic number, and b is a rational number, it has been shown above that ab is algebraic. This remains true even if one accepts any algebraic number for a, with the only difference that ab may take several values, all algebraic. Gelfand-Schneider theorem provides some information on the nature of ab when b is irrational. It states, if a is an algebraic number different of 0 and 1, and b an irrational algebraic number, then all the values of ab are transcendental numbers. Complex exponents with positive real bases. Imaginary exponents with base e. A complex number is an expression of the form, where x and y are real numbers, and I is the so-called imaginary unit, a number that satisfies the rule. A complex number can be visualized as a point in the plane. The polar coordinates of a point in the plane consist of a non-negative real number r and angle theta such that x equals r cos theta and y equals r sin theta. So the product of two complex numbers z1 equals x1 plus iy1. Z2 equals x2 plus iy2 is obtained by expanding out the product of the binomials and simplifying using the rule. As a consequence of the angle sum formulas of trigonometry, if z1 and z2 have polar coordinates, then their product z1 z2 has polar coordinates equal to. Consider the right triangle in the complex plane which has 0, 1, 1 plus x, n as vertices. For large values of n, the triangle is almost a circular sector with a radius of 1 and a small central angle equal to x, n radians. 1 plus x, n may then be approximated by the number with polar coordinates. So, in the limit as n approaches infinity, n approaches n equals the point on the unit circle whose angle from the positive real axis is x radians. The Cartesian coordinates of this point are, so Ex equals cos x plus I sin x. This is Euler's formula, connecting algebra to trigonometry by means of complex numbers. The solutions to the equation Ez equals 1 are the integer multiples of 2 pi I. More generally, if f equals w, then every solution to Ez equals w can be obtained by adding an integer multiple of 2 pi I to v. Thus the complex exponential function is a periodic function with period 2 pi I. More simply, a pi equals -1, x plus iy equals x. Trigonometric functions. It follows from Euler's formula stated above that the trigonometric functions cosine and sine are before the invention of complex numbers. Cosine and sine were defined geometrically. The above formula reduces the complicated formulas for trigonometric functions of a sum into the simple exponentiation formula using exponentiation. with complex exponents may reduce problems in trigonometry to algebra. Complex exponents with base e the power z equals x plus iy can be computed as x e iy. The real factor x is the absolute value of z and the complex factor e iy identifies the direction of z. Complex exponents with positive real bases. If b is a positive real number, and z is any complex number, the power bz is defined as ez lane, where x equals lane is the unique real solution to the equation x equals b. So the same method working for real exponents also works for complex exponents. For example, 2i equals ei lane equals cos plus I sin 0.76924 plus 0.63896 ia 0.54030 plus 0.84147 I 10 I minus 0.66820 plus 0.74398 I 535.49 I1. The identity is not generally valid for complex powers. A simple counterexample is given by: the identity is, however, valid when is a real number, and also when is an integer.